In the last video, we took a look at multi-lens systems, and we'll be working toward that goal studying the eye. But first, I'll start with a camera. And the reason for that is everyone starts the thing of saying the eye is like a camera. And one of the best things I ever picked out of one of my English classes was the professor pointing out that to say that something is like something is also to say that it is unlike it. Otherwise, it would be it. And usually the thing you're making the comparison to is the simpler system. And for the most part, this is the case here. So we'll start with a camera, and then we'll scaffold our way up to thinking about the eye. So I'll think about a camera system that just has a single lens, like so. Oops, try that again. There we go. Now, in practice, real-world camera lens systems almost always have multiple lenses. This is to deal with an effect called chromatic aberration that we'll run into later. We can go and take a look at it here and say, all right, usually you're going to have a relatively short focal length. And with a camera, you're going to have what's called the image plane of the camera, somewhere a little bit behind the focal length. So if I go and look at some distant object, say way out here, there will only be one exact distance where a distant object would come into perfect focus on the image plane. So let's just go ahead and locate it here. Oops. And I guess I'll have to move my image plane. There we go. So, and I could draw a zillion more rays. I won't at the moment. Actually, I will. So I drew two of the special rays, but there's nothing to keep me from drawing a whole bunch more rays that would all be going through to make my image. And if I happen to be at that one special location, everything's going to come into very sharp focus. But what would happen if you were literally anywhere else, if your object was anywhere else? Well, if that was the case, then the issue here is that these rays would not come to a sharp focus, but you can see that they would be typically coming together kind of close. So how sharp is sharp enough? Well, on modern cameras, the image plane usually has what's called a charge coupled device array, or CCD array. And as long as all those cones make a blur that is smaller than a pixel on the sensor, then that's just as sharp as anything else. So usually what camera manufacturers will do is they will characterize this with something called the F number of the lens. And this is the focal length of the lens over its effective diameter, which could be the actual physical diameter of the lens, or a camera manufacturer might decide to go stick some mechanical iris in order to cut off some of the rays that are going in. By doing that, they'll make the cone of rays coming in narrower. By making it narrower, you'll increase the extra distance that objects could be back and forth in front, be around the one perfect distance, and still have an acceptably sharp focus because it's all on the blur is the size of the CCD pixel or less. So from a sharpness perspective, the higher the F number, the better. It's saying that the diameter of the pencil is small, and you always have to say compared to what? The natural point of comparison is the focal length. Now, what if you decide that what you're taking a picture of isn't acceptably sharp? How do you adjust for that? Well, in a camera, the way that gets adjusted is you usually mechanically move the lens back and forth in order to bring it into focus. Now, one other thing about this F number thing that I'm mentioning too is you can also bring more and more things into focus, increase what photographers call the depth of field, increasing the distance around the object where things are acceptably sharp, by making the mechanical iris ever smaller. However, if you do that, every time you cut the iris down, its diameter down by a factor of 2, you've reduced the amount of light that hits the image plane by a factor of 4, because the light passes, because what counts is the area of the aperture. So this is why in cameras you'll see usually the f-stops on a lens are marked in increments of f numbers that change by a factor of the square root of 2. And this is so that each click doubles or halves the amount of light striking the plane, the image plane. Now with modern digital cameras, there's a third thing that you can put in, which is called the ISO of the lens. So you can increase the ISO, which is the sensitivity of the CCD array. You can make it more and more sensitive, but at the cost of introducing electrical noise into the image. The other way you can collect more light is just plain to have a longer shutter speed. So photographers will play with different choices of ISO setting, shutter speed, and F number of the lens to get whatever desired effect they want. Okay, so that's the camera. So now let's go and look at an eye, and I'm just going to apologize right now and say that I am in no way, shape, or form a medical illustrator. So don't, just putting that out there. So the eye is spherical-ish. I'm going to put a little bump right out here. So this bump right here gets called the cornea of the eye. And then immediately, immediately adjacent to the cornea is a different medium called the aqueous humor. And that should be kind of flat there if I can draw it a little better. There we go. That'd be the aqueous humor. AQU. Aqueous. AQUEOUS. Then behind that is the iris of the eye. So I'll draw that in like so. Then immediately behind that is the lens of the eye. Let's see what color we'll do. Purple for the lens. And again, sort of misshapen a bit, like that. Then attached to the lens are the ciliary muscles. What the ciliary muscle will do is it will flatten up the lens upon contraction. Then at the back side, to collect the image, you have the retina of the eye. And attached to the retina is the optic nerve. The retina is an amazing complex. It uses a collection of different photochemical sensors. Typically one set of what are called rods, which are very sensitive but only give black and white information, and at least two different sets of what are called cones, although there are different species where there's more than two sets, but for humans, two is typical, that provide color information, although they require a much brighter signal to give that. The density of these receptors is much greater in the center of the retina and much less out at the edges. Now, you had the same issue of how do you bring an image to focus on the retina. And this is done through what's called accommodation. In the eye, you don't move the lens back and forth. Instead, what you do is you use the ciliary muscles to flatten the lens, or if it relaxes, then make it wider. And by doing that, you can dynamically vary the focal length of the lens in order to bring things to a good focus. Now, to say good focus is stretching it a bit. It turns out that that between the cornea, the aqueous humor, and the lens, it's a compound lens system, all in contact with each other. The bulk of the refraction occurs at the cornea, but the lens is responsible for adjusting things. Turns out the actual image quality cast on the retina is pretty lousy. and the colors do not come to the focus at the same spot typically. Um, but it turns out that the brain does an awful lot of work to correct the image that is coming in on the retina to give it the nice sharp images that we see. Um, thus, a lot of our optical illusions. Okay. So, what could go wrong with the eye? Well, one thing that could go to before we dive into talking about what could go wrong with the eye, let me define a couple terms real quick. The near point of the eye is the closest distance you can focus. If you're a young person who hasn't had a lot of environmental stresses and all that, this distance is typically on the order of 25 centimeters. The far point is defined similarly. It's the farthest distance that you can focus. So again, for a young eye, that's approximately 3.8 million light years, the distance to the Andromeda Galaxy, which is the furthest object that the unaided eye can see. Let's just call that infinity and be done with it. So, what can go wrong? So, one condition you can have is what's called myopia. And the common English term for myopia is nearsightedness. And the thing to remember with that is that that's what works. So what this means is that what's not working is that the patient's far point, I'll say PFP, is less than infinity. So if you want to write a prescription, prescribe a contact lens, I won't bother doing eyeglasses because the spacing between the glasses and the lens complicates things a bit. You would write a contact lens such that the choosing a focal length such that the image distance would be equal to the negative of the patient's far point when the object distance is equal to infinity. This will be a diverging lens, so f less than 0. Something else that could happen would be hyperopia. And these, both myopia and hyperopia, are usually due to the eyeball changing shape so that the retina isn't located where the lens can accommodate to. So here, again, farsighted is what's working. So what's not working for the patient is that their near point is too far away. It's greater than 25 centimeters. So the prescription here would be to write a contact lens with a focal length such that the image distance would be equal to the negative of the patient's near point when the object distance is 25 centimeters. And that will correspond to having a positive focal length, so a converging lens. So one way you can tell whether your glasses wearing friend is nearsighted or farsighted is just to look through their lens. If what you see looking through it looks shrunk down, then you know that's a virtual upright and minified situation. That'd be case 4. That'd be a diverging lens, and so they must be nearsighted. On the other hand, if you look through and everything looks magnified, then that would have to be a case 3 situation, virtual upright magnified. That would be due to a converging lens, so you know that they would be farsighted. Added bonus would be if they have astigmatism. Astigmatism means that the eye also has lost some of its spherical shape. So they fix that by putting some cylindrical curvature into the lens as well. Some other things that can happen, probably my favorite named one is presbyopia, which if you break the Greek roots apart, it literally means that thing that happens to your eyes when you get old. What happens there is that the lens hardens, making it harder for the ciliary muscles to make the lens thinner. This has the result of pushing out the patient's far point. So what this winds up meaning is that you usually end up needing a prescription for every single distance that you want to look at. So either you're going to need reading glasses or bifocals or progressives, something like that. Other ones that you may have heard of include cataracts. The issue is that the lens is becoming opaque. This is usually due to ultraviolet light denaturing some of the proteins that make up the lens. The resolution for that is to do a surgical procedure where you replace the lens with a prosthetic plastic lens. And you may have heard of glaucoma. The vitreous humor, which is the fluid that is between the lens and the retina, the pressures can get to be too high and cause the nerves to die. And what's really pernicious is because the retina is thinner out at the edges, it's quite possible to not realize that you're losing your vision because the field of view is shrinking slowly from the inside. So this is why if you've ever gone into the eye doctor and they've done that thing where they blow the puff of air on your eyes, or they stick a device literally right on your eye where you see like a scary blue ring of light, what they're doing is they're measuring the pressure in the eye to see if they need to start to prescribe drugs to correct for that. Anyway, let's just do a quick example of this. Let's say you have a patient who is hyperopic. And their near point is 60 centimeters. So remember, hyperopia, hyper means far. That means that what works for them is seen far away. What doesn't work for them is what's up close. So usually what we want is the refractive power of the lens. So the nice thing here is that that's solving for 1 over f. So you can just plug straight into the most useful equation in optics, as long as we set up our DO and our DI correctly. So DO here would be 0.25 meters. That would because that's where we would like our object to be to match the young eye. And DI would be negative 0.60 meters. And that's because we want to park a virtual image out at the patient's near point in order to correct. So we can go ahead and grind that through. And get that the patient should receive a plus 2.3 diopter lens if we are doing contact lenses. Now, as a practical matter, they're probably going to be written for either like 2.25, 2.5, something like that, because these things come in standard sizes. As long as you get close enough, the eye's accommodation will be able to deal. Alrighty. So in the next one, we will get into other optical instruments that we can construct to make it easier to see either things that are really small but nearby or things that are really big but far away. Catch you in the next one.